In this video, we're going to do 4 examples of Ampere's law. And when we use Ampere's law, we're trying to find the magnetic field. So for each case, we're going to do a picture of the current source, an Amperian loop with its radius or sides labeled, include arrows on the loop representing the direction of both the magnetic field and dl. And we're going to show our values of B.dl for all parts of our Amperian loop, even if they're 0. So the first thing we're going to start with is a long current carrying wire. And the first one we're going to do is inside the long current carrying wire. So we're just going to draw a current carrying wire that, and we're just going to just exaggerate it to make it really thick. And we're going to draw our current density. So our current and our current density are really in the same direction. So this is going to represent either one, current or current density. So we'll just call this J or I, either one. And I'm going to switch, and I'm now going to draw my Amperian loop. So I'm going to draw my Amperian loop, let's say, like this. Okay, so when I draw my Amperian loop, I know if I point my thumb of my right hand in the direction of the current or the current density, then I know my fingers curl in the direction of the magnetic field. So I know on the part of the loop that's towards me, my B field is going to be like this. And I know, so this is going to be my B, and I know that my DL is going to be like this also. So that's going to be my DL. And same thing, this is the back of the loop, so my B field's going to look like this. That's B, and this is DL over here, same, DL. So the B and the DL are in the same direction, so I'm going to give these kind of vectors. And they're not curved, they're just little pieces that are a vector. It's in a direction, so it's really a straight line vector that is parallel at that point on the circle. So I also know that my radius, so let's go back to black. So my radius is going to be from here to here. This is my capital R for the wire. I also know I have a little r for my Amperian loops. This is going to be my little r. And so I'm going to draw, or I'm going to write out my equation. So I'm going to have B.dl. These are both vectors. This is a closed loop. And that's equal to mu naught I. And that's enclosed, meaning the current that's enclosed. And so I know all along my loop here, let's see if I pull this out and I do my mouse. So all along this loop here, I have B, which is a constant. So I'm going to be able to pull a B out. And then I have dl, so I'm going to have the integral around a closed loop of dl is equal to mu naught I enclosed. So my B and my dl is just going to be 2 pi r, the circumference of this circle. So I'm going to have B, oops, I lost my B, close that, there we go. So this is going to be 2 pi times a little r, because my loop has a radius of little r, and this is going to be equal to mu naught, and I enclosed is going to be J times the area. So remember that J is equal to I times the area, or sorry, that's I divided by the area. So that means I know that I is going to equal J times A. And in this case, we have J times pi little r squared. Because what I'm thinking about is in this loop of mine, in this loop I have over here that's inside, right, this is going to be the area. And so that area is just my little r squared. So it's the current that's going through that area like that. So I'm going to substitute that in here, J times pi r squared. So I can cancel out my pi's here. Oops. Hello. There we go. Looks like I'm losing syncing. Let's see, so I've got B times 2 and I had an r here, but that canceled, and I'm going to have mu naught times j, and I'm going to have an r here like that. Because my pi's cancel, so I guess I don't need this pi. Put the 2 back. So my answer is going to be B is equal to mu naught j over 2 times r. And that's going to be in the theta hat direction, because when I look at B over here, my B is going around the circle, right, like this. And so at each of these points, it's in the theta direction. So that's that. Now, if I want to, it also asked me in the problem to provide this in terms of I. So in order to do that, I'm going to substitute in. I know that J is equal to, for the whole wire, I know that J is going to equal I over pi capital R squared. So if I want to plug in for J, then that means I'm going to say that J is, I'm going to plug that in here. So I'm going to have B is equal to mu naught times I over 2 pi capital R squared on the bottom there times R, and still in the theta hat direction. So that way I can write it either way. Now notice, like, all of this, right, all of this is just a constant now, if I know what I is. And so I'm still, inside my B field depends on R in a linear fashion. So that means I'm going to have something that looks like this. And I'm going to have, say, if this is my R, then B is going to increase linearly with R on the inside. And so now if I want to do this outside, so here I've got, let's say I'm going to now change this a little bit. I want to go back to black. So now I'm going to have like a skinny wire, and my B field's going to be out here. So let's say this is my my current, and let's say my current is going this way. And then I'm going to draw let's draw my Amperian loop, say in blue, like this. I'm going to not do a dash line. So I'll do this. So this bottom part is on the front, is in front of the wire, and the top of the loop is behind. So I'm going to have, remember, if I put my thumb in the direction of the current, my fingers curl around in the direction of the B field. So I'm going to have the B field this way. This is my B, and my DL is right next to it. So DL, they're in the same direction. Here, same thing over here. This is my B. This is my DL. So if I go through and do this, let's label. So this is again going to be my R, little r. So I'm going to have the closed integral of B dot dl. Remember, these are both vectors in the theta direction. This is going to equal mu times I enclosed. So I can pull B out because it's constant around the loop. And now I have just dl, still closed, is equal to mu naught I enclosed. So B, the circumference, is my dl, so I'm going to have 2 pi r is equal to mu naught. Now I enclosed is just I, so B is equal to mu naught I over 2 pi r. You'll remember that that's pretty familiar. So and that's going to be in the theta hat direction, making sure that I remember that my B is a vector. So if I want to write this in terms of J, I can substitute for I can say that I is equal to J times A, which is equal to J times pi capital R squared. So I can plug that in, and that would be B is equal to mu naught J pi R squared over 2 pi R. My pi's cancel, and I'm left with mu naught J R squared over 2R. Fix that squared here. Squared. And so we can see that we still have the theta hat direction, And we still see that our B depends on this 1 over R. So if I go back to my little graph here, I'm going to have the B field is going to fall off like this. If this is the spot right here is where R is equal to capital R. And so this is just our radius. Our distance, actually our distance away from the center of the wire. Okay, so the next problem, it says that we have a solenoid. And a solenoid is just it's just a sleeve like this with wire going around it with current running through it. So we'll do something that looks like this. Make this go in front. That's not quite right. So we're going to go like this. And just imagine that there's lots of these wires. I'm just showing this as an example. So lots of wires, and my current is going to be going to the right. So I'm going to give my current to be in this direction. Okay, and so what would my loop be? I have to think about what my loop would be. But if I want to also think about what my B field would be. So I'm going to draw my B field in green. And if I curl my fingers in the direction of I, then my thumb represents the B field. So my B field inside this loop, this long loop of wire, right, is going to be an up inside. There's going to be no B field outside, so just a B field here up. And so what I need to do is I need to draw an Amperian loop. So what I want to do is I want to have, anytime I have an Amperian loop, I need to have current going through it. So I'm going to draw an Amperian loop that looks like, say, like this. And I can see that I have, or maybe let's do that a different color. So let's do that red. And I want to add another green arrow here just to make this pretty obvious. So I'm going to have a red Amperian loop that looks like, say, this. Okay, so that's my Amperian loop. So I've got my B field is going up this way, B field, and my I is going up, or my DL, sorry, my DL is going up. My DL is coming down here like that, but my B outside is equal to 0. And I don't have any B field on this part or this part, so I don't have any B field in that direction. So I still have B dot DL, close, oops, let me go back to black. Black, and so I have my closed integral of B dot DL is equal to mu naught I enclosed. And if I think about this, I have really 4 parts of my loop. So I have the part that's inside, which we'll call, say, 1. Also, this one is 1. And this is 2. And this side is 3. And this bottom side is 4. And so looking at those, the only place where B and DL are in the same direction, and we are going to get a value for our closed loop here is on the inside. So I'm going to have, say, B dot B times L. So we're going to call the length from here to here, the length of our loop, that's going to be L. So these sides are L. So BL, and let's say we decided on a square. So our loop is a square. So I'm going to have BL for side 1 plus BL for side 2 plus BL for side 3 plus BL for side 4. And that's going to equal mu naught I enclosed. So I know I have 1, and 1 has B and L together, but 2, 3, and 4, let me make that a different color to kind of make that obvious. So 2, this one goes to 0 because 2, right here, there's no B. B is only up right here, and so it's not in the same direction as my DL here, so that goes away. 3, there's no B out here. B is equal to 0, so this one goes away. Again, this is the same as the top. B is only in the vertical direction. It's not sideways, so this one's going to go away. So I just am left with 1. So I'm going to have B. And then L, so really my integral just becomes B times L. So this should say, I should actually turn this, let's say this is, each of these is really dl. So dl, 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 dl. And I'll cross this one out and that one out. There we go. So when I bring my b for this one here, I bring that out, and then I take the integral of dl, and that's just going to be L, the length of the side here of my loop. So BL is equal to mu naught I enclosed. So my mu naught I enclosed is just going to be, this is a solenoid, and so I have this number of loops n, right, and the number of loops per unit length. Okay, so here I'm going to say BL is equal to mu naught, and now little n is the number in terms of the number of loops. So I'm just going to have the number of loops times I. So each one of the loops that's inside here from here to here, so I've got like 1, 2, 3 in this example, but I'd have a lot more. So that would be like n is equal to 3. I would have that. So then I'm going to say B is equal to mu naught little n times I for the current in each one over L. And that's going to be in the z direction, because notice, right, my B field is up we're going to call this the z direction in this case. Now, if I wanted to also use the number of loops per unit length here, right here, right, I can also write that as B is equal to mu naught Ni over L, and I'm going to substitute N, or let me just fix that for a sec. So capital N is equal to little n, the number of loops, divided by length. So I can substitute that in for this part right here. So my B is going to be equal to mu naught capital N times I, again in the z hat direction. So I can write it either way. Next one, we're going to have a sheet of current. So I've got a sheet of current. So imagine I've got this sheet of current. Let's say it looks like this. And so let's say that my sheet looks something like this. I've got this current that looks like this, and you can check the AR app to see kind of more. If you're not really sure what that looks like, you can take a look. We're going to call this K. The current density here is K, because we got a sheet. And so we're going to draw our Amperian loop kind of like this. Let's draw it with red. So I'm going to draw it like this. And this is probably a lot easier to see in the augmented reality app too. But you can see the current's going to come through the area here, right? Through this area. And so what happens if I take my thumb and I put it in the direction of K, right? Then my B field is going to circle each one of those arrows that represent K. And so what's going to happen is I'm going to have a B field on this side. So let me just make it, I'm going to have a B field that looks like this. It's going to go down, and this is going to be dl. And I'm going to have a B field that goes up on this side. And you can check your hand and make sure that makes sense to you. And check the app, because that will help to kind of understand what it means. But I'm not going to have any B field on the top here or the bottom here. And that's because if you use your right hand rule, you'll see that each of the arrows on the top of one and the bottom of the other cancel each other out. So I'm only going to have it on the sides. So I'm going to have my closed, let's go back to black. My closed integral, b dot dl. Remember, the dot is for the dot product, so we need the b and the l in the same direction. Is equal to mu naught I enclosed. So I have 4 parts here again, and notice that 2 of the parts here, this one and this one, do not have any b in that direction. So I'm going to have 4 integrals. So we'll call this side 1. We'll call this side 2. We'll call this side 3. We'll call the bottom 4. So I'm going to have b dl of 1 plus b dl of 2 plus b dl of 3, oops, of 3 plus b dl of 4, and that's going to equal to mu naught I enclosed. And so here I'm going to cancel out, let's do that in red. So I'm going to cancel out 2 and I'm going to cancel out 4. So I'm going to be left with just 1 and 3. And 1 and 3 are the same, so I'm really going to have 2. My b is the same on the side, so that's going to come out of the integral. And then, now I have 2 because these 2 are the same, right? They're the same because they're on each side, the sides are the same. They're pointing in the same direction. They're pointing in the same direction, meaning b and dl are pointing in the same direction. So that's why they'll be positive. So 2bl is equal to mu naught I enclosed. So b is equal to mu naught I enclosed over 2l. Okay, and now when I want to figure out what k is, I know that I enclosed is equal to k times L. So that's my my current density, right, for my sheet. And I know that I is k times L. So I'm going to say B is equal to mu naught I enclosed is k times L over 2L. So then B is equal to mu naught k over 2. And so this, my L's cancel here. And this is going to be in the, we're going to call this in the y hat direction. And I'm going to call this y hat like that. And I'm going to say it can be plus or minus, because over here we can see that B on this side, B is in the negative y hat direction. And over here, B is in the positive y hat direction. So it can be in either one. And it's down on the left and it's up on the right. Okay, next we have a toroid. So this is our last one. So a toroid is like a donut. So what we're going to do is draw the donut, this. And we'll make this kind of big like that. And so what happens is we have this, we have current that's like comes down like that and then comes around, say like that, and then I'm terrible at drawing this, so kind of like that. This. So you can imagine like all the way around is going to be like that, and you kind of get the idea. So if we think about just the front like we did, let's say that the current is going down. So we'll have lots more in here. They're really tightly wound, so there's lots and lots of wires here, hundreds or sometimes even thousands. So let's say the current, all of them on the outside is down and on the inside it's up. We're going to call this our I. And now what we're going to do is, if this is a solid like donut, and then we're winding current around it, and so we're winding wire around it, and so our current is going is down on the outside. So if we put our if we think of a loop, we have a loop, and we put our fingers in the direction of the wires, right? So we have our fingers, and our fingers are pointing down. Our thumb is going to point to the right. So my B field is going to be pointing this way. Let me change that color. Let's make this red. So my B field is going to point this way, and so is my DL. My DL is going to be pointing that way too. And so it's going to look that way all the way around the circle. My B and my DL. And over here, my B and my DL. So it's going to be going around like that. So if I think now about my, let's go back into black again. So close loop, B dot DL is equal to mu naught I enclosed. So my B is going to be a constant inside this, my toroid, right? At the same place wherever I am on my, if I pick like say a radius like that, my B is going to be the same inside there around that DL. So I can pull that B out, and I'm just going to have closed loop DL is equal to mu naught I enclosed. So I'm going to have B times 2 pi r. And now my r is going to be from here to this is going to be my Amperean loop out to there. So that's r is equal to, now that's mu naught I. So we're going to use the fact that we have n turns, right? So how many coils, how many wires are wrapped around here? We're going to call it n. So we're going to say mu naught times the number of wires times the current going in each one. So that means I'm going to have B is equal to mu naught ni over 2 pi r. And that's going to be, again, in the theta hat direction because it's going around in a circle. Okay, so those are 4 examples. We have the toroid, we have a sheet, we have a solenoid, and we have inside and outside of a current carrying wire.